Welcome to another deep dive. We're tackling something today that I think we all use pretty much constantly, but how many of us actually understand what's happening behind the scenes?
Yeah, we're talking about the internet.
The internet, the digital world, cyberspace, the information superhighway, whatever you want to call it, I think it's safe to say that most of us use it every single day.
Absolutely. You sent us some really interesting source material for this one, a couple of transcripts from a YouTube channel called Code Curious, with a host by the name of Kathy Medina Deers. I think in one of the videos she also goes by Catherine Medina Devils.
Now that's interesting. Maybe it's like one of those Cher or Madonna situations where they just go by one name.
Yeah, it could be. Anyway, the videos are specifically titled APCSP 411 The Internet and APCSP 412 The Internet. So basically, we're using these to demystify the internet. Like, how does this massive network of networks actually work? Right. And these videos do a great job of breaking down some pretty complex concepts in a way that's easy to understand. They cover everything from the early days of computing to the nitty-gritty of protocols and how data actually travels across the internet. They even touch on the difference between the internet and the World Wide Web, which a lot of people get confused about.
Right, so not the same thing. We'll get to that. But before we dive into the internet as we know it, let's go back in time a bit, like way back to the early days of computing. We're talking huge room-sized machines that were basically isolated from each other.
Right, and as you can imagine, getting these early computers to communicate with each other was no easy feat. It was a whole different world back then.
So what changed? Like, what sparked the idea that computers should be able to talk to each other in the first place? Was it purely about sharing data, or was there something more to it?
I mean, initially it was definitely about resource sharing, like being able to access expensive hardware and software from multiple locations. But the potential for communication and collaboration, that quickly became apparent too.
Right, like researchers being able to share their findings with each other, or businesses being able to coordinate information across different locations.
Exactly. So the challenge then became how to bridge the gap between these individual computing systems and create networks where data could flow freely.
Okay, so that makes sense. But it's not like they were just sending emails back and forth, right? I mean, these computers didn't speak English or any human language.
No, definitely not. The videos emphasize this really important point. Computers communicate in numbers, specifically ones and zeros, which represent electrical signals.
Okay, so how does all the information we exchange, online text, pictures, videos, all of that, how does that get translated into this language of ones and zeros?
Well, think of it like learning a secret code. Every single piece of information, whether it's a letter, a picture, or a sound, has to be converted into these ones and zeros, which are called bits.
Okay, bits. Got it.
And then, to make things more manageable, these bits are grouped into larger chunks called packets. The videos use this really helpful analogy of a jigsaw puzzle.
Okay, I'm listening. I love a good analogy.
Imagine you want to send a jigsaw puzzle to a friend. Instead of just throwing all the pieces in a box, you put each piece in its own envelope.
Okay, so each envelope is a packet.
Exactly. And on each envelope, you write the address of the sender and the receiver. So that way, even if the envelopes arrive out of order, your friend can still put the puzzle together.
Right, that makes sense. So is this the difference between a computer system and a computer network?
Yeah, you got it. A system is like a group of components working together, but a network adds that ability to send and receive these digital envelopes, these packets.
So sending and receiving packets, that's what makes it a network. And this is where the concept of packet switching comes in, right? The videos talk about this.
They do, and it's a brilliant idea. Remember that "hello, how are you" example from the first video?
Yeah, where the message gets broken down into packets, and each packet might take a different route to get to its destination.
Exactly. And they might even arrive out of order, but the receiving computer knows how to put them back together. It's actually pretty mind-blowing when you think about it.
It is. I never really thought about how my emails or whatever get from point A to point B. I just assumed it was all like instant.
And that's the beauty of it, right? It all happens behind the scenes so seamlessly. And one of the key things that makes this possible is packet switching.
Okay, so it's more efficient and reliable because it's not relying on one single path for the entire message.
Exactly. If one path is blocked or congested, the packets can just take a different route. It's incredibly resilient, which is one of the reasons why the internet is so robust. And of course, none of this would be possible without routers.
Routers, those are the like traffic directors on the internet, right?
Exactly. They're the ones who read the addresses on those digital envelopes and figure out the most efficient path for each packet to take.
Okay, so we've got our data broken down into packets, and these packets are being routed all over the internet. But how fast can they actually travel?
That's where bandwidth comes in. It's essentially the speed limit of your internet connection.
Right, and the videos use a great analogy here. They compare bandwidth to the width of a pipe.
Exactly. The wider the pipe, the more water or data can flow through at once. Bandwidth is measured in bits per second, and the higher the number, the faster your connection.
So if you're trying to stream a movie or download a large file, you're going to want a higher bandwidth.
Absolutely. And the videos also talk about how bandwidth can affect things like latency, which is the delay between when you send a request and when you receive a response.
Oh, right, like when you click a link and it takes forever to load.
Exactly. High latency can be really frustrating, especially for things like online gaming or video conferencing.
So we've got our data in packets, it's being routed, and we know how fast it can travel. But with all these different computers and devices all over the world, how do they actually understand each other? It's like they need to speak the same language, right?
Absolutely. That's where protocols come in. Right. Think of them as the rules of the road for the internet. They're essentially agreements on how data should be formatted, transmitted, and received.
So without these protocols, it would be total chaos.
Absolute chaos. Like trying to have a conversation with someone who speaks a completely different language. The second video actually mentions a group called the Internet Engineering Task Force, or IETF, which is responsible for defining these protocols.
Just so it's like an international governing body for the internet.
Exactly. They're the ones who set the standards that allow devices from different manufacturers running different operating systems to communicate seamlessly.
Okay, that makes sense. And then the videos talk about the OSI model, which they call the mother of all computer protocols.
Yeah, the OSI model is a really important concept, even though it's not a specific protocol itself. It's more of a framework for understanding how network communication works.
Okay, a framework. So how does it work?
Think of it like a layer cake, with each layer representing a different aspect of the communication process.
Okay, I like cake.
And the videos focus on 4 of these layers: the network access layer, the internet protocol layer, the transport layer, and the application layer.
So 4 layers, each with a specific function. Let's start with the bottom layer, the network access layer. What happens there?
So this layer is all about the physical hardware, things like Ethernet cables, Wi-Fi cards, and network interface cards, or NICs.
Right, the actual physical connection.
Exactly. And each NIC card has a unique identifier called a MAC address, which is kind of like a serial number for your network hardware. At this layer, it's all about moving those ones and zeros across the physical medium.
Okay, so we've got the physical connection established. What happens next?
That brings us to the internet protocol layer, where packets really start their journey across the internet.
The internet protocol layer.
Right. And the key player here is the IP address.
The IP address, that's the unique address that identifies each device on the internet, right?
Exactly. It's like a street address for your computer or your phone. And routers use these IP addresses to figure out the best path for packets to travel across different networks.
Right, because these packets might have to go through multiple networks to reach their destination.
Exactly. The videos use this great analogy of passing notes in a classroom. You write the IP address of the person you want to send the note to, and then other people in the class act as routers, helping the note get to its destination.
Oh, I remember that analogy. That's a good one. And this layer is really important for the internet's flexibility and scalability, right?
Absolutely. Because packets can be routed independently, the internet can adapt to changes in network conditions and handle a massive number of devices.
Okay, so the IP address is the destination and routers are the guides. But how does our phone or computer actually get an IP address in the first place?
Great question. Most of the time, your device gets an IP address automatically through a system called DHCP, which stands for Dynamic Host Configuration Protocol.
DHCP.
Yeah, no, right? But basically, it's like your internet service provider temporarily assigning you an address so you could participate in the network.
Okay, that makes sense. So we've got the physical connection, the logical addressing with IP addresses. What's next in this layer cake?
Next up is the transport layer, and this is where we meet 2 very important protocols, TCP and UDP.
TCP and UDP. I've heard of these, but I'm not exactly sure what they do.
They both deal with data delivery, but they have very different approaches. TCP, or Transmission Control Protocol, is all about reliability. It guarantees that your data will arrive at its destination in the correct order, even if some packets get lost along the way.
Okay, so TCP is like sending a package with tracking and insurance.
Exactly. It establishes a connection first, kind of like a digital handshake, and then it checks to make sure all the data arrives safely. If any packets are missing, it resends them.
So that's why TCP is used for things like downloading files or browsing websites where you need to make sure you get all the data.
Precisely. Now, UDP, or User Datagram Protocol, is a bit different. It prioritizes speed over reliability.
So it's more like sending a postcard. You hope it gets there, but there's no guarantee.
Exactly. UDP just sends the packets out without any initial handshake or error checking. So it's faster and more efficient, but you might lose some data along the way.
Right, which is okay for things like streaming video or online gaming where a few dropped packets won't make a huge difference.
Exactly. And the videos also mention unicast, multicast, and broadcast, which are just different ways to send these TCP or UDP packets.
Oh, right, like sending to one specific device, a group of devices, or everyone on the network.
Exactly. So that's the transport layer in a nutshell.
Okay, so we've moved from the physical layer to addressing to data delivery. What's the final layer in this OSI model cake?
The final layer is the application layer, and this is where we as humans actually interact with the internet.
Right, this is where things like web browsers and email clients come in.
Exactly. This layer contains the protocols that our applications use to communicate with each other and with servers across the network.
Okay, so it's the bridge between the human world and the digital world.
In a way, yes. And the videos highlight two really important components at this layer, DNS and the World Wide Web.
Okay, let's start with DNS. The videos call it the Internet's phone book, which I thought was a great analogy.
It is a great analogy because remember, computers use IP addresses to identify each other. But we humans are much better at remembering names than numbers.
Right, I don't want to have to memorize a string of numbers just to visit a website.
Exactly. So DNS, or Domain Name System, translates those human-readable domain names like google.com or facebook.com into the corresponding IP addresses.
Oh, okay, so when I type in a website address, my computer is actually asking a DNS server for the IP address of that website.
Exactly. And then the DNS server looks up the IP address in its database and sends it back to your computer. It all happens in milliseconds, so you don't even notice it.
But without DNS, the internet would be pretty much unusable for most people.
Absolutely. It's one of those things that we take for granted, but it's absolutely essential for making the internet accessible.
Okay, so DNS is the translator. What about the World Wide Web? Now, the videos make a very clear distinction between the internet and the web. Can you explain that a little more?
Yeah, this is a common point of confusion. The internet is the infrastructure, the network of networks. It's the physical cables, the routers, the protocols, all the stuff we've been talking about.
Right, the underlying foundation.
Exactly. The World Wide Web, on the other hand, is a collection of interconnected documents and resources that are accessed using a specific protocol called HTTP, or Hypertext Transfer Protocol.
Okay, so the internet is like the highway system, and the web is the traffic driving on that highway.
Exactly. You need the highway for the traffic to exist, but the highway itself isn't the traffic.
That's a great way to put it. So when we're browsing the web, we're really just accessing a small part of the internet.
Exactly. There are many other applications that run on the internet, like email, file sharing, online gaming, and so on. The web is just one of them, but it's the one that most people are familiar with.
Right, because it's the one we use to access information, connect with friends, and do all sorts of things online.
Exactly. And the fact that the internet was designed to be so flexible and adaptable is one of the reasons why it's been so successful.
The videos talk about how the internet has evolved from small, local networks to this massive global network that we have today.
Right, and this evolution has happened organically, without any central control. It's a testament to the power of open standards and collaboration.
And the videos also mention IP addresses being typically 32 bits long, divided into 4 octets in the older IPv4 system. What's the significance of that?
So that 32-bit structure in IPv4 limited the number of unique IP addresses that could be created, which wasn't a problem initially, but as the internet grew, we started to run out of addresses.
Right, because now everything is connected to the internet.
Exactly. So that's why we're gradually transitioning to IPv6, which uses 128-bit addresses and provides a virtually unlimited number of unique identifiers.
Okay, that makes sense. So we've covered a lot of ground here. Let's try to sum it all up.
Sure. So the internet started with the need for computers to communicate and share resources.
And this communication happens by breaking down data into packets that are routed across the network.
Right. And the speed of this data flow is determined by bandwidth.
And underlying all of this is a set of protocols that ensure that different devices can understand each other.
And the OSI model provides a framework for understanding these different layers of protocols.
At the transport layer, we have TCP for reliable delivery and UDP for faster but less reliable transmission.
DNS translates human-readable domain names into IP addresses.
And the World Wide Web is just one of many applications that run on the internet infrastructure.
The internet is incredibly flexible and scalable, which is why it's been so successful.
It's amazing to think about all the complex technology that's working behind the scenes every time we go online.
It really is. And it all started with a simple desire to connect computers and share information.
So the next time you're browsing the web or sending an email, take a moment to appreciate the incredible journey that your data is taking.
It's a testament to human ingenuity and the power of collaboration. And this deep dive has really only scratched the surface of this vast and fascinating topic. What aspects of the internet's inner workings intrigued you the most? Perhaps the routing algorithms, the details of TCP's reliability mechanisms, or the evolution of internet protocols? There's a whole universe of knowledge to explore, and the digital world is constantly evolving, so there's always something new to learn.